We are recording the document. We
I
are
wonder,
documenting the process.
I wonder if Mars is gonna make it today.
I don't think so because I think he didn't catch up. So,
Right, he said maybe next week. I see.
chapter 4. This was very unexpected because chapter apparently whatever. Do you know how to pronounce this?
Let me scroll up. Chapter 4.
It's page
Ooh,
57 in the PDF.
lively categories. Not sure
Can you
on the
repeat the
ex
pronunciation again?
lively. I'm not
Nicely.
sure if the S is meant to be sounded out or if it's silent,
Yeah, but
but
the K is definitely silent in this case.
the K is silent.
Yeah, you just said Lisely, right?
Oh no, Clisely.
Oh, so there
Like
was a K in there.
there is a K, yes. Because
Lisely.
yeah, because I'm pretty sure, I'm not sure exactly where this name is from, but I'm pretty sure it's from the same region as the word, as the name Klein, as in Klein bottles.
Yep. Anyway, aside from the naming scheme, so we start talking about side effects. So we want to make a logger, which is a very common procedure in programming, right? So we
Yep.
want to make that happen, but we don't want to have them in a pure manner, right? So we don't want to have like a global or static thing floating around, and we're just
I
appending things
think,
into it.
actually, I think the more precise way to say it is we don't want it to be magic. We want it to be compositional.
I don't I don't know if the best way to describe it is magic, but sure. Awesome. So the way that we want to make it compositional, we need to embed this thing, right? But we discover very fast that it's very inconvenient to do that by hand because this is fine, but this is not so much because it is
Uh,
inconvenient that we have to do this by ourselves by hand every time.
by the way, you are not sharing the screen.
Oh yeah. Okay, my bad. There. I should be sharing the screen now.
Thank you.
So now, so this is kind of in the way, in the correct way, but we're gonna get rid of this thing because this is a little inconvenient, right?
Right.
Uh, because we're gonna have to do this every time, and this is like a marginal, a margin. It is a separation of concerns, right? We want to separate the concerns. So one thing is to do the functionality, and the other thing is to log it. Those things should not be glued together in the sense that when you want to do one, you are doing the other one as well. So the way that you're gonna solve that is by removing the let's say the accumulator from the argument of the functions, but we will still return the pair, right?
Right.
So then we have an example here of how to uppercase functions in C++, more C++, more C++ again, and then you're going to define an alias for this pair with a generic output and the string for logging as a writer, right? We're going to do that. And we're going to upgrade our functions to do exactly that. So we're going to do the two upper and two words. We're going to add their participation in the logging process by doing this thing. And it
Yep.
works. But then you're going to have this boilerplate here, right? Because we need to call one function, then grab the first thing out of the output of that, plumb that into the second function, re retrieve that output, and then combine them using like, I want the final output, but I want the combination of the logs.
Yeah,
Uh,
that gets really annoying really quickly if you try to do it by hand.
exactly. And what we're going to do here is to just compose them, right? We're going to abstract this boilerplate code out. Um, so we're gonna make so then we go to the writer category, um, which is basically trying to establish that this writer alias here establishes a category, which is kind of interesting. So what do we need? We need to compose it. We need to make it associative, and we need identity. So that those are the requirements.
Yep.
Uh, so let's see. Uh, okay, so here is the an example of how, like again, a more boilerplate on how we're going to compose them. The same procedure as before, but with different functions.
Yep.
This is actually the imperative description of what the heck is happening in this code. Um, and then apparently there is a very ugly way of doing it, which is this way of making the composition happening. And then there's
I
a
mean, it's C++. It's naturally ugly.
yeah, but isn't there? Oh, C++ 14. This is much better than the other one. This is much better. And then we can just do this right now. After we do all this, abstract this pattern out, we can just call the functions. And if well, I would make this a list instead of a tuple, because then you
That's not.
can continue doing the thing.
I mean, it can't really be a list because those things don't actually have the same type.
Mm. Okay, that's
It
true.
could be a list. It could be a list if C++ was dynamically typed, but it's not, so it can't be.
No, but that you're correct. You're correct. The list would be to have to be heterogeneous. That's true.
I
And then
mean,
we
you can also, I mean,
go.
you can also have an heterogeneous list in a statically typed
Yeah.
language
I know.
as long as it's dependently typed. But C++ is not dependently typed, so that's not gonna work.
Are you sure you need dependent typing though? Because I'm pretty sure there's a package in Haskell that does it. Pretty sure.
Uh,
I
I
think
mean,
it's cursed, but it exists.
the way it works in a dependently typed language, and this is what something I learned when looking at Idris, is that um, basically you define a type, which is a list that is actually made up of two lists. One of them is a list of types, and each type corresponds to the type of the value that's in the other list that holds the actual
Then
values.
you zip them.
You just carry them together, actually.
Ah, okay. That's cool. Now we're gonna go to the identity of the writer, which is pretty much the empty string, right? So how do you do this morphism of going to the same thing? It's very easy. You just grab the input, return that as the first member of the pair, and the log does nothing. But if you pay close attention, this should remind you of a monoid, hmm? Because we are having empty, and in this particular case of the writer, the process of combining them is string concatenation, right?
Yeah,
Which is very interesting. And then he mentions that the composition is also associative.
because monoids
Yeah,
have an associative
yeah,
append operator.
yeah. And then we're gonna do the same thing but in Haskell. And then there we have the famous fish operator that allows us to to compose the writers. It's
Yep.
not surprising that its implementation is like this. It is supposed to be like that. Um, what else? What else? This is the identity thing.
The famous return from Haskell.
Yeah, no, but I think there will be a very much greater reason than like how can I say? Uh, because this is gonna be removed or renamed in some GHC version in the future. But I think in this book there will be a reason to call this return.
No, it's because I don't actually recall if this is mentioned in this chapter or not, but Lisle categories are actually the category theory. Like this is how you represent a monad as a category.
Yeah. But as far as I can tell, the reason that this is called returning monads is because of just time. Because monads were not defined as being applicative in the first place. That was discovered
Yeah,
afterwards.
yeah, yeah.
This name and the peer they get confused. Although I like it because then you can trick your imperative friends without explaining what this does, and that's cool. Uh, because then you can jump teaching stuff. Like you want to teach other stuff first, and then they will see this return and think it's exactly as they believe it is, and they are wrong, but that doesn't matter because they will not ask. Uh,
Uh,
which is
yeah.
awesome. Anyway, so then we have the same uppercase and two words functions in Haskell, of course. And then apparently we talk about these Kleisli categories, which is based on a monad. I don't want fully understand what he means by this specifically, because he made a writer, which is cool. But what exactly define? What is the core characteristic of this type of category? That's the thing that
Uh,
my understanding is that it needs some like these categories, the morphisms of these categories have some embellishment. Although, as he explains himself, this is a very loose term. What the heck does that mean? I have no idea.
like, if you think about it, if you go, he gave the concrete example of a writer, right?
Yeah.
The return value of functions that returns writer, it returns a writer of some other type, right? There's a wrapper there,
Yeah.
a writer type constructor in this case. But the composition operator for a Kleisli category, it preserves that wrapper, but it doesn't concern itself with it when you're just gluing functions together, right?
Yes.
Uh, Because the point, the point of
Oh, yeah, that reminds me of the bind. Yeah, 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 yeah.
yeah, because you see, if you have a function, an arrow from A to B, and an arrow from B to C, composing them gives you an arrow from A to C, right? But there's this writer thing in the middle, and what makes it a Kleisli category is that we say, okay, there are some rules that we can kind of ignore the fact that there's this pesky writer in the output that the input doesn't want,
Mhm,
and
mhm.
that gives you a slightly different composition operator from just the normal arrow composition from.
Okay, so my perspective now that you describe it in that way is that there is a channel in which the composition is still being maintained, but you have other potentially multiple other channels in which stuff is happening, but this marginal stuff is not forbidding you from focusing on making the composition.
Yes, exactly. Because if you just try to use normal function composition,
It will
if you
break.
have a function from A to writer B, and you have a function from B to writer C, that doesn't fit
Yeah,
because B and writer B are different types.
yeah, yeah. That's what he says, and makes sense. But
But if
now I have the intuition though, so the embellishment is like a marginal channel, marginal channels happening on the side, but they are not touching the composition aspect of it.
yes, you need to have a different composition operator that acknowledges the fact that yeah, concretely we do have this thing that's around the B return type, right? This writer thing, but
Yeah.
there is a way to still compose just the B that we get out of this and preserve the information that is passed to the writer wrapper.
Yes. Very cool. Very cool. I get. I liked it. I have intuition now. And blah blah blah. So later on, this embellishment correspond to something called endofunctor, which I have no idea what it is. I do know the meme, but I don't know what it means.
I mean,
Uh,
endo just means inner, so it's a functor that goes back to where you came from.
yeah,
Like
no.
it points.
The taxonomy of the word I can understand, but I don't have yet an intuition of what functor means in this domain. So we're gonna get
Uh,
there.
yeah, we're gonna get there. I could give you a spoiler, but I think this is actually included in what we're reading today, so I won't.
The
I
functor,
will
no, it's
wait.
not included.
Oh, it's not?
No, not included. At least chapter six. I read four, five, and six, and I know
Oh,
this
right.
this is
It's
not
in
touching that.
chapter 7, actually. It's next week. Oh, in that case, I'll give you a slight spoiler. You know how in category theories you compose an arrow with another arrow? As
Yeah.
long as the end of the first arrow
Mhm.
points to an object
Yeah.
that's in the tail of the next, right?
Yeah.
A functor is an arrow that goes from one category to another.
Wait,
Naturally, that gives us, yeah,
so it is
if
like an
categories,
upper level.
yeah. So instead of having a category of normal objects, the way we were doing right until now, you will have a category where the objects are themselves categories, and the arrows between those categories are functors.
Yeah, okay, okay, so I see. So if you're talking about arrows between objects, we call those morphisms. But if you're talking about arrows between categories, we call those functors.
Yeah, a functor is just a morphism where it goes from a category to another category.
That's nuts. I'm excited to read that. Let's see, let's see.
Yeah, and there are certain restrictions, like you have to preserve some structure in the categories. So it's not just any plain old morphism that is a functor. Or we'll get to that when we get to chapter 7.
Okay, so let's continue here. That's a nice spoiler. Uh, so okay, and then we are done with chapter 4. So chapter 5, which is where, well, at least to me, the real, well, more new terminology and definitions come into play. Uh, so something that is very interesting, which is apparently is called universal construction, is that you're gonna define an object not using the object inner guts, but how it relates to other objects, which is kind of weird. Anyway, so apparently this is universal construction. Uh, so then we're gonna go with the first definition, which is the initial object. And here I have my first question to you.
Okay.
So when I read initial object and terminal object definitions, my first intuition was going back to that weird lattice abstraction that we talked about someday last week. And the top and the bottom, these
Yeah, that's
definitions
actually
remind me of that.
yeah, that's actually a good intuition. Yeah, it is. It is a good intuition actually, because what characterizes a lattice is that you have some objects from which, and here I'm going to use a slightly more categorical interpretation of a lattice, where you take the arrows as being, category arrows or morphisms. Uh, in a lattice, the top object is the one that has all the arrows going out of it, except the identity arrow, of course. Um,
So he's the initial object.
yes, it would be.
Okay. So he's the initial object. Interesting.
And the bottom is the one that has all the arrows going into it,
So he's
again,
the
except
terminal
the
object.
identity. So it would be the terminal object, yes.
Very interesting. And I believe the morphism in this case would be I don't know, maybe for a more concrete example, the partial, if you have a partial order with like a less than, right? So
Yeah.
maybe that would be the morphism in the case of the book
Or
that I was showing you.
yes, it would be. It would be.
Ah, I see. Well, at least I'm trying to see. Ah, okay, okay, okay. And just for for the recording purposes, I know shit about the lattices. I just know they are weird and they have uh, very cool topology. That's the extent that I know about them.
Look, a lattice is just a partial order, except you have a distinguished top element that is greater than every other element, and a distinguished bottom element which is smaller than every other element. That's it. That's the only thing that distinguishes a lattice from a plain old partial order. You have a top and a bottom. That's it.
I already mentioned this to you. That doesn't explain the very weird shapes, but you already told me that they do this just because they make it fancy. Because
It's
the
because it's a partial order. There's no guarantee that you can take any arbitrary two objects from that order and compare them, because it's partial. It's not total.
Yeah, I understand that.
That's Yeah, that's where the weird shapes can come from.
I'm gonna try to read it again, and now with your description in mind, maybe I'm gonna understand it finally. Let's continue here. So the initial object is again, we are using universal construction, so we're defining objects, we are naming them based on their relationships, and and this label here, initial, is because this object has one and only one morphism, not a single instance of it, but it's the same. There is a difference in there. So you can have n any amount of of the same morphism if they are going from that to any other object in the category. So that's the initial object. And these pictures are awesome. They look
Yeah.
so good. Okay, so now so then we have some examples here.
Oh, oh, oh,
Go.
oh, oh. Here is also where he starts throwing around the word isomorphism.
Yeah, but
Remember
I
that,
understood. I think I understood what that means.
no, 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 but remember that word because it's actually very important.
Yeah, no, I know. We this word is very important, like even as outside of this domain. But at least now I got a more precise definition because I always went by intuition. This, if I understood correctly, I think I got it. Uh, anyway, so then we're gonna have an example here. Uh, so in the category of sets and functions, the initial object is the empty set, right? And the empty set in Haskell is the type void, and the reason is because there's no member of the set, right? So this morphism here can never be called. But it is going from that set to everybody else.
Yep.
It is doing that. And then to make it symmetric, I guess we're gonna go with the terminal object, which is the object in which everybody else is going to by the same morphism again. But it is everybody is going to that. Naturally, this guy is represented by units, right? Because everybody, this morphism here, everybody from all the types can go to unit. Hence,
You know, you
go.
know, I just realized something kind of funny actually. If you look at it from a category theory perspective, then unit is the bottom because all the arrows point to it, and void is the top because all the arrows come out of it.
Yeah.
If you look at it from a type theory perspective, it's backwards. Void is the bottom because it's the subtype of all types, and unit is the top because it's the supertype of all types.
Mmm. I didn't notice that. That's maybe there's something in there. Well, I'm gonna have to think about it. But you're correct. That's interesting. And then we have a counterexample here because you may say, why does this need to be unit? Why not bool? And the reason is because you can have these are two morphisms and this is not the same, which means it is not terminal. Which is cool.
Yeah.
Then we're gonna go to duality, right? Which is basically grabbing the entire graph of objects and its arrows and reversing the direction of all of them, right? So it's a there's a functor that does that, profunctor.
It's it's opposite day. Yeah.
Anyway,
It's not. It's not. Is it a functor?
no. I'm not talking about these functors. I'm talking about like Haskell profunctors.
Oh, right, right, right.
So I discovered that there's many functors. It's like a family. And
Yeah.
maybe there is a functor that goes the other way around. But I don't know profunctors. I'm stupid. I don't understand these. I understand bifunctors, normal variant functors, but any contravariant. Oh, it's the contravariant. It is contravariant. Uh, see? Contramap.
Oh, right. It takes a function from B to A and returns a function from f of A to f of B. It's backwards.
Yeah. Which is really weird. But if you want to take a look at it, there's a really cool FP complete article about it. This one. So documentation purposes, if you want to read this is gonna give you some intuition about it. I still think they are weird by nature, but they're like it helps. But the boss is profunctor. I don't understand profunctors. Anyway, going back to the book here. So we're gonna call this property of being able to be reversible, invertible. How do you call this?
Uh, I guess reversible is as good a word as any.
So duality. So then if you have this morphism and this composition, if you revert everything's going to be reverted, including the composition. I don't understand the pun that he did here. No op. What is the joke here?
Well, reversing the identity arrows is a no-op, right? Because he's using op to denote the inverse morphisms up there in the text.
Ah, okay. I didn't notice that one. Sure. We're gonna call this the duality thing with the prefix co. So we're gonna have products, co-products, monads, co-monads, cones, co-cones. But if you do co twice, that goes back to the original one. So co-monads is actually just monads. And then we're gonna go to isomorphism, right? Which is a very, very famous word, very strong word to say. Uh, we started by talking about equality, which it is still a very complicated issue even nowadays. Uh, and
Um,
how are we gonna define it, right? How are we gonna define it?
Personally, I'm a big fan of operational equality, but that's kind of annoying to compute for functions. So there's that.
Well, when you mean operation, you mean like the the mapping between domain and codomain is the same.
No, no, operational equality is actually something from the metaprogramming literature, um, where basically you need to be able to tell if two languages are equally expressible or equally expressive, or if one is more expressive than the other. And operational equality just means, okay, is there any context that can tell these two values apart in this language?
Hmm.
If there isn't, then the two values are operationally equal because the language cannot tell them apart. So they are effectively the same value.
Hmm. I see. I see. Okay. So the intuition is that isomorphic objects look the same. They have the same shape, which is a very loose definition. It means that every part of one object corresponds to some part of another object in one-to-one mapping, right? So mathematically it means that there is a mapping from object A to object B, and there is a mapping from object B back to A, and they are the inverse of each other. Of course, this mapping are in here are morphisms. So an isomorphism is an invertible morphism, or a pair of morphisms in which one is the inverse of the other. So let's continue. Let's see an example here. Right. So let's see an example here.
Yeah, this definition in terms of composition and identity is actually pretty good. I like it a lot.
Uh, so this one is the inverse of. We understand the inverse of in terms of composition and identity, right? So if we do, if the morphism G is the inverse of F, if their composition is the identity morphism, that seems reasonable, right? That seems
Yeah,
fairly
because
reasonable.
because if you do a thing and then do the same thing backward, that's the same as doing nothing.
Uh, okay, so something happened. Okay, so going back after a very not nice technical difficulty thing. Um, so here we're gonna define that the two things are the inverse of each other if they when they compose they go identity. Yeah, sometimes you can't do it, right? Well, sometimes you cannot undo it, right? Because like if you make a cake, you cannot undo the eggs; they are done. But some other times you can. So here, this is a very natural definition. Here's the drawing of that. Something happened with this PDF because I'm pretty sure this was supposed to be composed, and it has this, but whatever. Uh, so notice that uh, so there is a catch in this proof though, because this word, yeah, because we're gonna use that fact here. Because if there are only two morphisms, one from 1 to 2 and 2 to 1, and we know that they compose an identity, that means that one must be the other, I think. Um, yeah, so that's the important thing. So not only is the initial object unique up to isomorphism, it is unique up to unique isomorphism. So that's important because apparently you can have more than one isomorphism. Uh, okay, and now we're gonna go to products, which is the starting of my problems. So let's start by first talking about Cartesian product. So it's talking about a set of pairs. So I believe when it's a set of pairs because each pair is a combination of every single possible combination two y's. Cool. Um, and then we're gonna have two functions which have very interesting names called projections. And then these are very famous first and second functions. So these are their types and definitions. You can remove the type signatures. You can use wildcards. This is the C++ version. Nobody cares. Here's where my problem starts. So it's saying here let's try to define a pattern of object isomorphisms in the category of sets that will lead us to the construction of a product of two sets A and B. This pattern consists of an object C and two morphisms P and Q, connecting it to A and B respectively, right? So we need these two guys, P and Q, in order to make it happen. Very important. Very important. Then all C's that fit this pattern will be considered candidates for the product, right? So we need an object and we need two functions. That's cool. There may be lots of them. Yes. For instance, let's pick int and bool and get a sampling of candidates for that product. So here's one, int. Can int be considered a candidate for the product int and bool? Yes, it can. And here are the projections. So he's proposing to make int in this case is C. Is that it? Okay. C and A. Okay. No, actually that's not true. It's just a coincidence in this case, right? Because this A could not be this one. Yeah. Yeah. So then you're gonna make the projections P and you're gonna make the projections Q. And B is gonna be the Boolean. Because we want to make this is the product between A and B. So A is int and B is bool. And the C is gonna be integer. So here are the candidates for the projections. And as it says, it matches the criteria. So this is matching as a very specific criteria. There is a C, there is a P, and there's a Q. I want us to remember that when we're talking about more concrete examples later on. Because for me, my difficulty is mapping what he's saying in the practical examples to these three requirements. So here we're going to have another example. It's a type of three elements. This is going to be our C, and we want again A and B to be integers and bools for our Cartesian product. So here we have the P, and here we have the Q. It works. And then he says, You may have noticed that while our first candidate was too small, it was covered in the int dimension of the product, the second was too big. It duplicated the int dimension. I don't know what that means. Int and bool. Doing nothing. Okay. So then we're gonna go to the definition of quote better, right? We want to be able to compare these candidates, right? Because we have at least two instances of having a C, a P, and a Q that fits the criteria. So how are we going to differentiate them? How are we going to make them in a how are we going to put them in a scale? And the suggestion here is that we would like to say that C is better than C prime if there is a morphism M from C prime to C, right? We want to say that. We also want its projections to be better or more universal than the projections of C prime. What it means is that the projections P prime and Q prime can be constructed from P and Q using M. So basically, if your projections are utilizing my projections, I'm better. Yeah. So if we are distant in terms of definition from a composition with M, that means that the one with this P and this Q, it's better than the one with the P prime and Q prime. And here's the image, right? So it's basically saying that if this P prime or in Q prime, if they are an M factor with composing with P and Q respectively, they are weaker. Okay. Um so there's a term called factorizes. I have a question. Is M unique? No, not necessarily. Not necessarily. Okay. And then we demonstrate that we can factorize the weak candidate using first and second, in fact, which is very interesting. So this is the like abstract, and this is the concrete example in our case. So we are going from an int, right? We are going from an int, which is our C, right? But here's the no, this is C prime actually. This is C prime. So there is a P, there is a Q, and if we can define an M and compose with first and second, that means that the int is weaker than int bool. Okay. And we go through that, right? Because then we rewrite P and Q, which are the outer ones, using first and second with M, using this M. Okay, my mouse started for a moment there, so maybe I should not use the dock for USB. Maybe that's an issue. But okay. Um, we were able to show. No, but it's saying the opposite. You see, it's saying that the int bool is better than the other two. The m for the second example was similarly uniquely determined. This is for the triplet, right? We were able to show that int bool is better than either of the two candidates. Which candidates? But as far as my understanding goes, uh, oh, the int and the triplet, these are the candidates. Okay, then in that case, I just read it wrong. That is the case. We show that. Blah blah blah. So here we go in more detail about the case of the triplet, I guess. Um, that makes the Cartesian product our best match, which means that this universal construction works in the category of sets. So now we're going to go to the definition. A product of two objects A and B is the object C equipped with two projections such that for any other object C prime equipped with two projections there is a unique. So M it is unique, right? unique morphism M from C prime to C that factorizes those projections. So this is the definition, right? So we need a C prime, four morphisms, P, P, Q, P prime, Q, Q prime, and we need A and B. Those are the requirements. A coproduct, on the other hand, right, is the reverse of the directions of the arrows of the product, which basically means doing from instead of C to A and B, we're going to have A, B going to C. And the ranking of better is also going to be factorization. So it's also going to be inverted. So in this particular case, wait, it's going to be inverted. Is the object C is better than object C prime that is equipped with the injections I prime and J prime if there is a morphism M. Yeah. No, the direction is, but the better guy is always in the middle. Yeah, so how can I say it? In the other case, the arrows were pointing to A and B. That's fine. But the better guy was the yellow one in the middle, if that's the case. In here, yeah, but it is still saying that instead of doing I prime, you can do I composed with M, or in this case, M after I, which basically means that you are me plus M. There is, we're gonna have to stop on chapter 5, unfortunately, because, well, I told you what's happening today and people entered here. But there is another definition of like better that I learned in previous semesters in my masters that is very similar to this thing, but it's talking about something completely else. But I can talk about that later on. And then a coproduct of two objects A and B is the object C equipped with two injections, such that for any other object C prime equipped with two injections, there is a unique morphism M from C to C prime that factorizes those injections. No, 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 but that's chapter 6, and that's where more confusion from my part comes in. Because I still need to understand the practical examples that I think is going to be. Yeah, it is in fact talked here. So in the category of sets, the crow product is a disjoint union of sets. Give me the A, the B, the C, P, and Q. What does this mean? Yeah, but I still don't see it because as far as I can tell, the definition is pretty clear. You need many things, and saying this does not address any of that. I know because chapter 6 talks about it again. But if I don't understand, because he's not going to explain it, he's not going to pinpoint this is A, this is B, this is C, this is C prime, this is P prime. He's not going to list it to me, so I can't follow the definition. I need. It seems to me that at this point he expects the reader to have some intuition. No, 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 no. Let me rephrase it then. I think he expects you to have intuition about both of them. both of them, product and co-product. But because I don't have it, and I'm only trying to grasp what the definition means at this point, I cannot just do this jump. So what is, why is maybe? Why is that the case? The I and the J, these ones, the ones on the right. Sure. M is what? Sure. Yes. I'm still confused. Let's go back to what you said before. So the I is left and M is going to be whatever? And what is I prime? So you have a left from an either. You have a function from an either to a whatever, and you have a left of the whatever. Uh, I see. And I guess this is right from the either. This is the either. This is the same as before, and this is the right from the whatever. Um, so in that particular case, hmm, uh, A and B are both values from the either. Uh, C and C prime are or B. Well, yeah, yeah. Mm. Uh-huh. Okay, so I'm gonna kind of like do a little jump because I want to go back to this to talk about the case of disjoint unions and for the case of the programmer, which is using tagged unions. I want to go back into that. I don't have the time, but let's just jump that for a moment. We can bring this back from that example, and we have a symmetry as well. So I don't remember what this is anymore. Uh, do you remember? For yes. Okay. I think I got it. I think. So if they are not different, if they are not that different, they are symmetrical. Is that the point? Hmm. Okay, so this is actually pretty interesting because it's basically, I think it's this chapter that talks that unit is basically doing adding nothing to the process or something like that. Yeah, no, yeah, that's gonna be developed in chapter 6 by a long shot. Oh, oh, okay, I can take a look into that. Okay, so there are a little bit more definitions here that I'm jumping because he's going to talk about surjective when the functions are tightly filled their domain, and when they are, I believe, when they are feeding one another, they are called injective. Anyway, so I'm going to have to come back into this. I'm sorry that I had to finish this earlier, but well, shit happens. So I'm going to finish. Yeah, no, that was not fun. I'm going to finish the recording now. Start recording. Okay, it's
That was
another
a
day.
yes.
It's a different day. It's
Hello, future people.
we didn't finish last time, so 2 weeks have passed, and we are gonna do tomorrow more chapters. But today we settle on finishing 5. And as far as I remember, last time in a hurry, I was confused about these intuitions about products and co-products, but Marinho helped me figuring those things out. Um, so just to be very short to people that already understands it, and I was only the only stupid one that didn't. Uh, so the way to interpret these figures right here, the way to interpret these figures right here is that this thing, which is a product, you are basically all combining information. So in order to go to have these two things here, um, like in order to have a boolean and an integer, you need to have them together. I think that was the interpretation that we settled on, right, Maninho?
Yeah,
In order to you to project something out of yourself, you need to have that thing within, right?
basically. That's the intuition.
Yeah. So and this the arrows here just basically mean that if you have an M, and as far as I can tell, the definition says that it needs to be unique. If you
Yes.
have an M and you have the P and a Q, you, they say that you can factor things out by using M composed with another function, with another morphism. So
It's M composed with, in this case, first and second, right?
yes, so you can factor out P by using M composed with first and Q by M with second.
Yeah.
And that basically means, for the programmers out there, basically means that what we are doing here as a product means that we are combining information. Because the product is the yellow, okay? So the
Yeah.
product is the yellow. And the co-product, but it needs a little bit more creative imagination to get the intuition. But it basically means that in order to you to have this C co-product, you need to gather information out of one of two possible things. So you can receive stuff from A or receive stuff from B. But if there is an M that can, an unique M that can factor out these injections, I prime and J prime using I and J with composition, C is a co-product.
Yeah, and
And
then again has to be unique. Same
M
thing
has to be
as
unique.
before.
Yeah. So what that basically means is that products uh, are basically combination of things, combination of things. Um, and co-product is more like it has a more alternative notion, right? Because you can grab stuff from one um, one object, or another object, A or B.
Yeah,
So in order to, C only needs to have one of them in order to compose with M and go to C prime. And that's
yeah,
basically what matters. So the co-product example is the disjoint union of sets which needs to be tagged. That basically means that the final outcome of the disjoint is going to be all the elements from the two original sets, but tagged with their source set.
yeah.
Tagged with their source set, and we can replicate this thing using tagged unions in programming. So here we have a C++ example in which we have the
Yeah.
tags and we have the morphisms.
Note that the text does say this, but C++ doesn't have tagged union, so you have to kind of roll your own by using an enum.
Yeah, and I believe that how can I say this? I believe C++ doesn't fix the C problem and that you can mix and match the enums with the unions, right?
Yeah,
You can make a mess.
you can make a mess.
Yeah, nothing forbids you of doing this function here and putting is email here, right? That's
Yeah,
basically
that's
what
an
it is.
annoyance with C
Which
and C++.
apparently Zix fixes, right?
Yes, in Zig, you can do the same thing that you're doing here and just say, yeah, this is a struct, it contains a tag and a payload.
Yeah.
But Zig does have tagged union, so you can say, okay, for this particular tag, the payload is of this type, and the compiler will check it. So,
Yeah. So this
but
is
it
a.
doesn't, yeah, it
Mhm.
doesn't do away completely with the C style, because for low-level stuff, sometimes you need that. And Zig is meant to be a replacement for C, but it does give you the better option of, yeah, this is checked by the compiler, it's tagged, and it's nice.
Yeah, so in Haskell you can combine stuff, take the union by separating the structures with a vertical bar. So this is basically a co-product, and we are talking about co-products right now. And this is actually a more generally defined as the integer type.
The canonical co-product in Haskell is either A or B.
Yeah, and this is in a factorizer example, which I believe is basically coding the picture. This.
Yeah, basically.
Okay, and then to finish chapter 5, we have asymmetry. And this is basically talking about how things that you would expect to be symmetric aren't symmetric. So it starts by saying that the co-product is very different from the product. As an example, he used the size of finite sets. So the size of the product of in the case of finite sets is the product of the size of the individual sets, and the size of the co-product is the sum of the sizes. And if you're having trouble understanding what this means, it basically means that if you have an either, I think we're gonna use I'm gonna use the same example that you told me, Marinho. So either boolean boolean, how many options can you have there, right? So you can have four.
Or, yeah,
But if you have either void boolean, uh, and this is a product, and it's saying that the size of the
it's a
product is the size of the individual sets. So we're gonna have either void boolean, which is zero is the void, is the size of the void,
that's
and
the
boolean is
sum,
two.
it's a co-product. You're
Either.
talking about co-product.
Oh
Either is
no,
the
sorry, sorry.
co-product.
No, no, sorry. I said it wrong. Either is a co-product. It is a co-product. So it's gonna be
Yeah,
zero
either,
plus two.
yeah, because there are no values of type void, otherwise it wouldn't be the type void, right?
Mm-hmm.
Which means that you can never reach the either from the left. You can only
Exactly.
reach it from the
So
right.
you're gonna have right true and right false, and those are true. So you have zero plus two, which basically means that we have uh, the size of the co-product is the sum of the sizes. So before we had either boolean, it was 2 plus 2, and now we have 0 plus 2. And the
And if you
product
try the same,
example is gonna
yeah,
be
if you try the
like,
same thing for the product, if you try the product of Boolean Boolean, that's also 4 because 2 times 2 happens to be 4.
let's use a tuple.
A tuple, like more than 2 elements, a larger
No,
product, I
no, let's
guess.
no, no, no. Yeah, it can be more than 2 elements, but I was more thinking, what is the product size of a tuple void boolean?
Well, it's 0 because to build that tuple, you need to come up with a value of type void, and there aren't any. So
Yeah,
it's
so
0 times 2.
exactly 0 times 2, which is what I was aiming for. So you're gonna have 0, and that is exactly what it's saying here. It's the product of the sizes of the individual sets.
Yeah,
So
and if you're wondering, the number 1 is played by the unit type and the unit value.
yeah, yeah, but we saw this before with the initial object, terminal object stuff.
We did, just for
Uh,
completeness.
then uh, he talks about this also being the case of like initial objects and terminal objects, right?
Yeah, and he mentions here about the asymmetry that like when you have the void type, there are no arrows going into it, right?
Yes,
But for the unit type, which is the
terminal.
there are actually arrows coming out of it. So
Yes.
that's because functions are not symmetric, and he explains why in the following page.
Yeah, he also explains that you can have a more, I would like to say, he provides an example on how you can view products as a more, I don't know.
Yeah, like before when we were doing the universal construction for products, he gave us the example of a triple, right? Why a triple is worse than a pair. Here he's doing the opposite. He's showing why unit is worse than a pair, and it's because units as a product is not general, right? If you have a first P and Q for units, they only give you one possible value by definition because like it's a functional unit.
Yeah. So yeah, so this is basically an example of what exactly what Marinho just said. But then we go to the and then he contrasts that with the co-product, saying that there is no simple interpretation, like simple interpretation meaning all of this for the co-product. Again, to
Yeah.
emphasize on the asymmetry of these things, and and then he talks about the cause, which is the functions. Functions are not symmetric also. And then to summarize this last page here, basically he's classifying the functions based on relationships between the domain and the codomain.
And
So
the
he
input
established,
and the output.
yeah, input and output. So if you have a domain that is smaller than the codomain, he says that he's going to call those functions that are mapping elements from the domain to the codomain as embedding functions. So you can imagine them as like the domain is kind of like in like wrapped. Like I imagine the codomain like being greater than the domain, so being like this. Uh,
Yeah, it's like you have the domain,
and
and
I
because
think
it's
it's
smaller
is this
than
my
the
internet? Let
domain,
me
you're
check if it's
basically
my internet.
saying,
Hello, hello.
oh,
I think it's your internet, dude.
oh,
I think you should leave the call and join again.
okay, one sec.
Okay. Technical difficulties. I apologize. I'm probably not gonna cut this. At least not. Well, hello, hello, hello. Okay, Maria is still not back. Hello.
Okay, can you hear me?
Keep talking.
Can you hear me?
Yes.
All right.
Okay, let me
So
share my
where
screen
were
again.
we? Where were we? Asymmetry, right?
Yeah, we were talking about
Embeddings.
that.
Yeah. So like if the output set is larger than the input, so the codomain is larger than the domain. Function basically says, okay, here's how you can take the domain and put it inside of the codomain, and you basically map like elements from one to the other.
Yeah. So I hope Marinho's audio was not bad. Like it was glitching a little bit, but I think it's the message still went through. But there's not that's not all. So let's imagine that you have also functions that are doing what he calls it collapsing. And what that means is that you're mapping members of the domain to the same elements in the codomain. That basically
Classic example, a function that returns Boolean.
that classic example. Your audio is glitching, dude, and I don't think it's my internet.
Yeah.
A classic example, as Marinho said, is a predicate, right? Because the predicate picks a value of a type A and returns a boolean. So it's mapping all the elements of the domain to the codomain with only two elements. So this is collapsing. And not surprisingly, composition of collapsing function is even more collapsing, right? So imagine that you are composing a predicate with a function that picks a boolean to unit. Imagine that for a moment. If you compose those, you're going to have effectively composed a function that maps the entire domain of the type A to unit. Um,
Yep.
Collapsing functions have a special name, which they are called injective. The
Actually, that's
op
no collapsing. Yeah,
uh,
no collapsing.
oh, no collapsing, sorry. Non-collapsing functions are called injective. The opposite of embedding, for like apparently mathematicians like the opposite of I just to give it them names. It's called surjective. And then if you are neither of embedding or collapsing, you're gonna be a bijection, which is apparently a synonymous with isomorphism.
Oh, it's an isomorphism when you're dealing with like functions, right?
Yeah,
If you're dealing with relations or other kinds of arrows that are not functions, that may or may not be the case, but for functions, it is an isomorphism.
yeah,
It's basically a function that you can reverse and get back the original thing.
yeah. Uh, so that is to say that functions are in general are symmetric, right? So if you just change the direction of the arrow being a function, it's very unlikely that's going to be symmetric because functions have all these types of patterns or slash behaviors, if you want to call that. That they can be embedding, they can be the opposite of embedding, so they can be surjective, they can be collapsing, they can be non-collapsing or injective, and if they are not embedding nor collapsing, they are bijections. So they have all these options, so that when you reverse, you need to pay attention on what you're reversing, because you
Yeah,
may have
and
a problem.
in case you're wondering, this is something that came up when Lemon and I were talking. There isn't actually an expanding function because that would actually
Yeah.
leave the realm of functions into non-determinism
Yeah,
because
so
you
I,
would
I
be
asked
mapping the
Marinho
same
about that.
inputs to two outputs.
Yeah. Sorry, again, Marinho, sorry to interrupt you.
Fine.
Um, so I asked Marinho why this sounds very strong to say this thing because you're basically saying that if I'm not embedding, which means that my codomain is not bigger than my domain, so they are like one to one, and if I'm not collapsing, I'm not doing funneling, I am doing bijection, which means isomorphism. But what about if the domain is like doing like this, like the opposite of a funnel? But then Marinho said, yeah, but that wouldn't be a mathematical function, wouldn't it? Because that's a non-deterministic function now. So maybe that's worth mentioning. That the at least to me the intuition that I have right now is that you need to be one of those three, because there's no way around it. Or you are one-to-one mapping bijectionally, or you are funneling, collapsing it, or you are embedding. So
Yeah.
That's my understanding,
and
right?
and that's the end of the chapter. But yeah, this is actually pretty interesting, and it goes a bit deeper into the correspondence between like products and co-products to numbers a bit later
Yeah, we're
in
gonna
I
talk
think it's
about that
chapter.
tomorrow in chapter 6.
Yeah.
Okay, so I think this is all we have for chapter 5. So I'm gonna finish the recording now.
Bye.